Hey guys, welcome to part 2 of analyzing resistor networks. I'm going to take a step back in this second part from all the complicatedness of loop equations and just get real simple. Now, there's a couple of really important rules you got to follow here. So, first one is if you've got two things, whatever they may be, in series, they always receive the same current. Well, what about, no, they always receive the same current. Well, I know that, no, they always receive the same current. All right, they will, however, split the volts. All right, and that's getting back to that loop equation idea that we talked about, where if you've got, say, 2 or 3 different resistors, then between them, they will use up or split the volts of the battery. All right, for parallel, they get the same volts, and they will split the current. All right, and again, that gets back to Kirchhoff's second law, his junction equation, which said that when you have current coming into a junction, it breaks apart into not necessarily equal parts. Okay, as an illustration of this idea, I've drawn 3 resistors in series, so maybe I should say plus R3 up there. Okay, now if I have some amount of current coming through this wire, right, it has to go through this one, then this one, then this one. That's it. All 3 of those absolutely must receive the same current because there's only one path for that current to follow, and electrons aren't going to disappear in the middle of the wire, or ever anywhere for that matter. All right, but the splitting volts idea is this, right? If you had, let's say, 9 volts back at the battery to start with, this one might use 3, this one might use 4, and this one might use 2. Okay, all right. Now, there's an analogy we can use for this to help people understand why they will all have to receive the same current and use different numbers of volts. It looks like a staircase. All right, now this should look familiar. I've used it in another video, or it might not if you haven't seen that video. In this particular case, I was using it to illustrate things with capacitors or whatever, and I've only drawn 2, let's call them staircases. In this analogy, height corresponds to volts, because that's kind of what it is, right? Height is related to gravitational potential energy. Volts are related to electrical potential energy. So height and volts are kind of at least related concepts in terms of energy, all right? So in our analogy, volts is like height, okay? So over here on the left we have, an elevator which is lifting the people up onto this higher platform. The elevator is like your battery. Okay, that's what it does, is it provides energy, it gives input. And in this analogy, the people are the charges, all right? So here they are, or here's one guy anyway, at the top of the stairs, a charge ready to go moving along the path that has been set before him. Well, this first staircase here is like a resistor, right? He loses a certain amount of energy as he goes down that staircase. That's like the resistor using up a certain number of volts. And then, well, he has no choice. He has to go through the very next one, and then that one also uses a certain number of volts slash energy, okay, whatever. And now you can see he's gotten back to the ground. So in my picture then, there's only 2 resistors. There's 2. Forget what I said about that third resistor. There's not a... Okay, so in this case, right, if this first staircase, let's say, it looks like it's about 3/5 or something. All right, let's say that one used up 4 volts. And the other one's a little bit taller. It used up 5 volts. There we are. We're back down on the ground. Notice, of course, that it is impossible for a different number of people to go down the first staircase than what go down the second one. It's literally impossible. There's only one way back to the ground. Well, I guess there's 2. You could... Okay, no. That's not... Nope, nope. Right, there's only one way back down using the stairs, right? And so, therefore, everyone in this analogy that goes down this staircase has to go down this one. That's like how all of the current that goes through this resistor must also pass through that resistor. There isn't another way through. In a parallel arrangement, of course, we know that the current splits, right? The current comes in some of it goes this way, some of it goes down the middle, some of it goes the other way. And frankly, it's probably not going to split evenly, okay? If one of these resistors is huge, like say 100 ohms, that's not actually that big, but whatever. The middle one is, let's say, 50 ohms, okay? And then the bottom one is 25 ohms. Well, I know which way I'm going if I'm an electron. I'm going to go through the 25 ohm path. And they will, in fact, split according to a ratio here, where some of the current, most of it, goes through the 25. Half as much goes through the 50, because that's twice as much resistance. And half again as much goes through the 100 ohm resistor, again, because it's a factor of 2 that things are different by. All right, now, most people are good with that idea of the current splitting at the junction, and also even splitting by ratios. What people usually have a little more trouble with is the idea of the volts being the same for all three of these resistors, right? They look at this and they're like, well, what do you mean the volts are the same? How can that be? I mean, you know, like they've got different resistances and different currents. How can you tell me that all three of those resistors have the same volts? Or maybe they have this other idea that, you know, if they know there's like 9 volts left, they think that each one is going to get 3 volts or something, which would be splitting the volts. Well, that's not how it works. If this is all hooked up to, let's keep it simple, a 9-volt battery, all three of them get 9 volts. They all three get 9 volts, meaning the difference in energy between either of those 2 points there, right, those 2 junctions that I highlighted, is 9 volts. All three resistors, even though they have different resistances and get different currents, are all going to get 9 volts. All right, to help us understand that, I'm going to reference the staircase analogy again. All right, again, as you can see, there's the elevator, the battery, which is going to lift things up, lift the people who are the current moving through the circuit. All right, but here we have at the top 3 different paths, right? Some people are going to elect to go down the extremely dangerous staircase. All right, some are going to go this way. All right, and then the people who are the least thrill-seeking are probably going to go down this much more gentle one, right? Okay, whatever. I'm not going to worry about, in terms of the analogy, which one is a large or small resistance. The point is, there's 3 different paths, but notice, since they're all going back to the ground, they're all the same height. So even though they have different, quote, resistances, right, if it's the same elevation back to the ground, then it's 9 volts no matter which way you go. All right, oops. And so let me get back to the... There we are, right? So it's 9 volts then, no matter which way you go. Whether you take this path, or that one, it's the exact same number of volts back to the battery, back to the ground. So now that we've got some kind of a theoretical understanding of how this works, I'd like you to find example 7 in your notes packet. Example 7 looks like this. We're comparing 2 different circuits, which are, they've got the same 3 circuit elements, but one's connected in parallel and one's connected in series. So what you should do is pause the video and do what you feel like you're able to do. Certainly everybody should be able to find the equivalent resistance. And then continue the video when you are ready. Okay, so to begin with, the equivalent resistance should have worked out to 1.5 for that first picture. And therefore, the total current is going to be 6 amps. So notice I'm just using Ohm's law that you used a couple of homeworks back, right? If the battery provides 9 volts against those 2 resistors and their equivalent resistance is effectively 1.5 ohms, that's going to give us 6 amps of currents after a little bit of division. Now, please note, since these are in parallel, neither of them actually receives 6 amps. If I want to figure out how much current each one actually receives, I have to go back to that idea I mentioned moments ago. Resistors in parallel receive equal volts. All right, so see if you can figure it out now. What's the current through each one? That would be IA and IB. All right, now this time I have written it in the format of a loop equation, which if you're like, whoa, hold on, what happened to V equals IR? All right, I'm trying to get us used a little bit to doing loops because we'll be doing a lot of loop equations. The loop I'm following is dotted in red there, right? I'm starting with the 9-volt battery and then saying minus IR for resistor A. Now, there's a couple of things that you can note from this. I did not pass through resistor B. I don't care. Didn't go through it. It doesn't matter. For that loop, all that matters is the battery and resistor A. And so therefore, I kind of, in this particular case, wouldn't actually need to have done all this stuff. For other circuits, it's very necessary to find the equivalent resistance, but if it's pure parallel like this, you can just cut straight to it. All right, so we've got 4.5 amps through resistor A. All right, if you couldn't get that one on your own, well, now you should be able to find B. Pause me, find B, see if you're right. There we have it, resistor B, 1.5 amps. All right, now what about VA and VB, which are the other two things that that example asked us to find? Well, we ought to know that they're just 9 volts, because that's what we said they would be. But if for some reason you have to calculate the volts used by a particular resistor, remember that it's just Ohm's law, V equals IR, and if we plug in, we will in fact get it's 9 volts. They use 9 volts each. All right, so a couple things to note here. Remember we said same volts for parallel, okay? And then the other thing is we said that the current splits when you have a parallel connection. And they don't split by some random amount. They split by, in this case, a factor of 3. Well, that's not a coincidence, that the fact that those currents are different by a factor of 3. If you look back at the prompt, it said that the resistances were 6 ohms and 2 ohms. And the 4.5 amps goes with the 2 ohm resistor, right? More current through the smaller resistance. And the 1.5 goes, of course, then with the larger resistance. All right. Note also that those two individual currents add up to the 6 amps. All right, so they had to split by a very specific ratio based on the resistances, and they had to add up to the total current because of Kirchhoff's junction law, right? Current in equals current out. Now let's take a look at the series one. I think probably you don't have too much trouble saying the equivalent resistance is 8, all right? But see if you can do the rest based on what we've talked about so far, and resume me periodically as needed. All right, based on Ohm's law, we're going to have a significantly smaller amount of current going through here, because the equivalent resistance was much greater since they were connected in series. Now, what about the currents through each of the resistors? That wording might be troubling you a little bit, because you might be thinking, I thought they get the same current, and you would be right. That's exactly the point I'm trying to make. So I hate that it comes across as sort of a trick question. It's not meant to be. They receive the total current. So whereas in the parallel one that we did first, neither A nor B receives I total. They each receive their own individual currents, all right? But in this one, both of the resistors receive the total current because there's only one path around the circuit. All right, now what about the volts? Use the method that we did moments ago, Ohm's law, to calculate the volts used by each one, and you'll see that they are not 9 volts. Yep, so there we are. Those are the results. However, you should notice something interesting about the two voltage values. Taken together, they add up to 9 volts because the battery supplied 9 volts, so between A and B they had to use 9 volts. So in series, the volts get split according to Kirchhoff's loop law, which says all the volts must get used up as you go around the circuit. And then, I guess the other larger point was that since they're in series, they each receive the same current, all right, but split the volts that were coming to them. All right, now we're going to take a break here and proceed onward to the next video, which will cover example 8, which is a slightly more complicated circuit that will require us to actually learn loop equations and junction equations.